Okay, so previous video we introed you to acids, bases, what they are, how to recognize them. Talked about the Arrhenius theory and the modified Arrhenius theory. So today we are going to look at strong versus weak and mono versus poly. Okay, so when we talk about acids, right, we said that acids have hydrogen and they are going to ionize to produce that hydronium ion for us. So the difference between a strong acid and a weak acid basically comes down to how much of this reaction actually occurs. So what we find is that for strong acids, this reaction goes to completion. So when we say something goes to completion, that means all of the reactants turn into products. So once this reaction is done, I will have no HCl left. It will all be converted into hydronium and chloride ions. So what we actually find is for acids that there are actually only 6 acids that do this, that react all the way, where all of that acid gets converted into hydronium and whatever that anion is. Okay, so those 6 strong acids are the ones listed here. Okay, so they are perchloric acid, hydroiodic, hydrobromic, hydrochloric, sulfuric, and nitric acid. The other way you will notice this is if you go to that acid table that's at the back of your booklet, these are the first 6 that appear in there. Right, so here's that table in your booklet, right? You'll notice that the first 6 here, which are above this grayed out one, are the ones that are your 6 strong acids. Okay, so no need to memorize those. They are in your data booklet. You always have access to your data booklet. So it's really just a matter of remembering that everything above the grayed out bar is a strong acid, which means that everything below the grayed out bar is what we call a weak acid. Okay, so whereas strong acids entirely get converted into products, what we find is for weak acids, it's only some of them that get converted into products, right? So if, let's say I had, I don't know, let's look at phosphoric acid. I would find that once I put that phosphoric acid into solution, I would still have H3PO4 molecules left over. Whereas with any of these ones, I put them into water, I don't have any of those molecules left because they're all going to get converted into hydronium and whatever the negative ion is over in this column. Whereas for something that's down here below it, I'm going to convert into this negative ion and hydronium, but I'm also going to have some of this left because that reaction doesn't go to completion. Okay, so how we're going to be able to show the difference between something being strong and something being weak is the type of arrow that we use, right? Remember, we use these arrows in solution. We said a single-headed arrow was for an unsaturated solution because all of the reactants turned into products. But we said that for saturated solution, because some of that original solute remained, we were going to use that double-headed arrow to show that some of that was still there. So when we talk about weak acids, we also use a double-headed arrow. And that's because we still have some of this original acid in the solution. We do have some of this, and we do have some of this, but not all of that weak acid actually got converted into products. Some of it did, but some of it didn't, which is why we're going to use this double-headed arrow, right? And remember that that double-headed arrow also means that we are in a state of equilibrium. Okay, remember, equilibrium was when 2 processes happened at the same time that were the opposite of each other. Okay, so if something is a strong acid, when I write that ionization equation, so if it's one of these 6, I'm going to use one of these types of arrow, right? I'm going to use a single-headed arrow. But if I have a weak acid, and I'm going to recognize it's a weak acid because basically it's not one of these 6, then I'm not going to use a single-headed arrow. Right? We're going to use that double-headed arrow instead to show that it doesn't go to completion. Okay? So what that can mean is that 2 acids that are the same concentration can have different pHs. And that's because pH kind of gives me an indication of how strong or weak something is. So generally what you're going to find for acids is that stronger acids are going to have lower pHs. And weaker acids are going to have a little bit higher pHs. They're still going to be under 7, right? Because if we're hitting 7, then we're neutral. But they're not going to be as low as a strong acid is going to be for the most part. So same thing holds true for bases. We also have strong and weak bases. So these ones, you do kind of have to just know which one are strong and which ones are weak, because there isn't really a data table for me to look at for that, okay? But what you find is strong bases all contain hydroxide. Okay, so those 3 non-classic bases we talked about the other day, like ammonia, sodium carbonate, sodium hydrogen carbonate, they're all going to fall as weak because they don't actually have hydroxide in them. Okay, then what you find is if that hydroxide is combined with a group 1, so any metal that's in that first group down your periodic table, it's going to be strong. So like sodium hydroxide is strong, potassium hydroxide is strong. Same is true for group 2. The only exception is beryllium. Beryllium is not a strong one. It is weak. Okay? So any metal out of group 1 or group 2, with the exception of beryllium, paired up with hydroxide is a strong base and is going to get that single-headed arrow. Anything else is weak. So any other metal with hydroxide, so like beryllium hydroxide, aluminum hydroxide, those would be weak, and we would be using that double-headed arrow. Okay? And same deal for our non-classic bases, right? So ammonia, which is one of the ones we talked about yesterday, actually gets drawn with one of these, a double-headed arrow. And that's because it's a weak base. This reaction doesn't go to completion. So we find the same thing that we do with our acids with respect to those pH numbers. Those really strong bases can have pHs close to 14 or even 14 or maybe even bigger than 14. But our weaker ones, like ammonia, are going to be smaller. Okay, they're not going to be less than 7 because, again, 7 is that neutral point. But like ammonia, for example, usually comes in right around 9. And that's because it's a weaker base. Okay. So next thing to kind of look at is monoprotic and polyprotic. Okay, so we talk about things as being monoprotic and polyprotic both for acids and bases. When we use these words, mono means one and poly means more than one. Okay, protic in this case is referring to a proton. Remember when we talked about hydrogen, we said hydrogen is only composed of a proton and an electron? Well, when we produce a hydrogen ion, that's technically a proton, right? It's lost its electron. It's only a proton. So when we're talking about a monoprotic acid, that means it's an acid that more or less has one hydrogen and is going to produce one hydronium in solution. When we're talking about a polyprotic acid, that means it's going to make more than one hydronium in solution. And usually that happens because it has more than one hydrogen that it's capable of losing. So oftentimes when we look at a formula, right, if I look at HCl or HBr or HI, they all have only one hydrogen in them, right? Which is why they're all considered monoprotic acids. Okay, same is true for HF and for acetic acid, right? And sometimes you guys look at acetic acid and you're like, but Ms. Chip, there's 4 H's. I should be poly. But what we find is this is the only H that we can lose. And that's because, again, if you think back to bonding, remember we said carbon always needs to have 4 bonds? If we start taking some of these H's away, that carbon isn't going to be attached to 4 things, and we can't have that, okay? So why we group these separately is because these 3 are strong, right? They're in that top 6, and these 2 are weak, which is why we've grouped them separately. So you should be able to recognize whether something is strong or something is weak, and whether it's monoprotic or polyprotic. So to decide strong or weak, we're looking at our data booklet. If it's in the top 6, it's strong. If it's not, it's weak. To decide mono or poly, we're basically looking at how many hydrogens does it have in it. Okay? So we look down here, we have sulfuric acid, right? This has 2 H's. That's why sulfuric acid is polyprotic, because it can lose both of those H's. So what we find when we are dealing with those acids that are polyprotic is they lose these hydrogens a little bit differently than some of our other types of compounds do. And what happens is we have to take one hydrogen off at a time. So although this has two H's in it, right, we're not just going to suddenly break this apart into 2H plus and a sulfate. We have to take them off one at a time. So what you find is for polyprotic acids, you have to write as many ionization equations as you have hydrogens that you can take off. So for these 5 up here, I would only have one equation to write because they only have one hydrogen to lose. But for sulfuric acid, it has 2 H's, so I need to write 2 equations. So first ionization equation is going to be this. We're going to have that sulfuric acid reacting with water. It's one of our 6 strong, so we get to use a single-headed arrow. It turns into that hydrogen sulfate and that hydronia, okay? So we took one H away, turned it into HSO4 minus. You'll also find that if you look in your data booklet, that when you look at that H2SO4, in the column next to it is HSO4 minus, right? So that also can help you figure out, oh, okay, this is turning into this. It's at the top of the page, so it's strong. I get to use a single-headed arrow. So now I still have an H left, right? I have that HSO4. So we have a second equation to write, and that's that HSO4 minus reacting with water. So HSO4 minus is now a weak acid. And I know that because, again, when I go back to my data booklet, here's HSO4 minus as an acid, right? It's in that acid column. It's below the grayed out area, which is how I know that it's going to be weak. Okay, that's why I'm going to use that double-headed arrow that we used. And now I get to turn it into that sulfate ion, okay? So make use of your data booklet. You have it, and it has a lot of information in it. Okay, so it turns into that sulfate ion. I know I'm done now because there's no more H here, right? It doesn't have an H, so it can't be an acid anymore, okay? So if I was dealing with phosphoric acid, right? Phosphoric acid, if we think about that, it's H3PO4. I would have to write 3 equations for that one, and I'd have to write 3 equations because there's 3 hydrogens to take off, right? Again, you go to that data booklet, here's that H3PO4, it turns into H2PO4 minus. Then we go down that table and we're looking for the H2PO4 minus. It's not on this page, I want to say it's on the next one, right? So here's that H2PO4 minus, it's turning to HPO42 minus. This still has an H. So now we're going to find this in the acid column again. And oh, look, now it's all the way down here. And that's going to turn into that phosphate ion, okay? So as many equations as you have hydrogens that you need to remove, okay? So mono versus poly based off of how many H's you can take off. Strong versus weak for acids based off of where it shows up in that data table. Okay, we also talk about mono and poly for bases. These tend to be a little bit more obvious, especially with bases that actually have hydroxide in their formula, right? I can look at sodium hydroxide. There's only one OH in there. That's going to be monoprotic, okay? But if, let's say, I had, I don't know, magnesium hydroxide, right? That would look like that. And so that has 2 OHs. So that would be polyprotic because it has 2 of them. Okay, we also find that with some of those non-classic bases. Here's an example for you. It's not a great example. And the reason I say it's not a great example is this one tends to kind of confuse you guys a bit. And just because you're like, where are things going? Probably a better example would be that carbonate ion, right? Remember we talked about carbonate in that last lesson. So carbonate, sorry, I'm having issues, looks like this, right? And if I react this with water, it has 2 negative charges, okay? So this is going to get a double-headed arrow, and it's going to get a double-headed arrow because it's not one of our strong bases, right? It doesn't have hydroxide in it, so no way it can be strong. So first step, it's going to accept 1 proton, so it's going to turn into an HCO3. Now it's only going to have 1 negative charge because it took a proton, which has a positive charge. Okay, and then that is going to combine with hydroxide. So there's our first hydroxide that we make. Okay, now this actually works somewhat similar to our polyprotic acids, and that this happens in a stepwise fashion. And that's only true for weak ones. If it was magnesium hydroxide, I would literally just go and I would go to this and I would break this apart and I'd be like, here's my magnesium ion. And then here are my two hydroxide ions. Okay, but when I have those non-classic ones, they are going to go into that stepwise fashion. So down here, now I would take that hydrogen carbonate ion. Okay, I would react it with water again. Okay, still weak. So using that double-headed arrow. It's a little bit bigger of an arrow, that's okay. And making H2CO3 because we gained one more proton plus another hydroxide ion. Okay, so not generally going to ask you to do this in Chem 20. Usually if we're asking you, it's going to be this, or we're just simply asking you, can you recognize mono versus poly? So do you know that you're actually looking for, does it make one OH, does it make two OHs, three OHs kind of thing? Okay, so spills and neutralization. When it comes to spilling either an acid or base, we kind of have two ways to deal with it. So one way is to dilute it, right? We talked about dilution in the last unit. We said basically just add water, right? The other option is to neutralize it, right? So let's say I had spilt a strong acid, I could neutralize it by using a weak base. We generally don't want to use something that's strong to neutralize it because then we have another hazardous spill that we have to deal with. So whether you dilute it or neutralize it, it kind of depends on where do you spill it, right? And how strong is what you have spilled. So let's say like a train is carrying something, a chemical, and it falls over and the chemical starts to leak. Usually we're then just going to choose to dilute it. And that's because we don't want to introduce more chemicals into an environmental situation, because then it's just probably going to cause more issues, right? We're probably just going to choose to just add a whole bunch of water. It's going to dilute that acid or base to the point that it just becomes neutral and it has not really any issues, right? Situations where I might choose not to do that. Let's say I spilt some chemical on the lab bench. I'm probably not going to choose to dilute it because I'd be pouring so much water, I'd then make an entire mess of my lab bench, probably make an entire mess of my floor, right? That's where I'm probably going to choose to use some neutralizing powder. So a lot of the times when we choose to neutralize it, we have like little powdered containers where there's one for acid spills and one for base spills, and I'll just kind of shake it out onto whatever it is I've spilt. It will neutralize it, and then I can just wipe it up and get rid of it, okay? So generally, if it's spilt on something like that, you're going to go with the neutralize it option. If you spill something on yourself, it really depends what do you spill on yourself and how strong is it. Okay, if you spill something that's pretty weak, you're just going to go right ahead and you're going to dilute it. If you get something on yourself that's pretty strong, then you're probably going to look at taking something and trying to neutralize it. Just to be able to counteract it. But again, you're going to be really careful with what it is that you pick to neutralize it, because that can cause a lot of issues on its own. Obviously, the idea would be not to get any on yourself, so that then you don't have to actually worry about that, because chemical burns are extremely painful and can definitely have some lasting long-term effects that are not always so great. So, neutralization. You guys tend to forget about neutralization. We spend so much time talking about ionization equations and dissociation equations that you forget that neutralization is very much a thing, right? And if you think about Science 10, when we reviewed Science 10, we talked about our 6 types of reaction, and neutralization was one of the ones we talked about, where we said that we combine an acid plus a base, they neutralize each other to make water and that ionic compound, right? So here you have an example, right? We take nitric acid, we combine that with sodium hydroxide. It's going to neutralize, where that H is going to come off of the acid, and the OH is going to come off of the base. Those two go together to create my water over here. And then I'm left with my ionic compound, right? The cation is going to combine with the anion, and there's that salt, in this case, sodium nitrate, okay? So please make sure you don't forget about neutralization reactions, because you guys tend to, and then when we ask you to write a neutralization equation, you guys start doing weird things with like dissociation and ionization equations, which really isn't what we're looking for, okay? So things you should be getting out of this is, how do I identify whether something is strong or weak for both acids and bases? And how do I recognize whether something is mono or poly, also for acids and bases? And then what does that mean for when I write those ionization equation or I write those dissociation equations? Because moving forward, we're going to start getting into the calculations, right? If you think of solutions, we kind of talked about dissociation equations, and then we started calculating molar concentration. To eventually be able to get to our pH calculations, we're going to have to be able to calculate concentrations of hydronium and hydroxide ions, which means we have to be able to write those ionization and dissociation equations correctly so that we can make sure that we get those right ratios for when we get into those calculations.